In this lesson, we shall learn about piston engines. Every pilot begins his career in flying on a piston engine plane. Understanding it will make you a professional pilot. Piston engines are also known as reciprocating engines. Most widely used on aircraft used for basic training. There are still a large number of planes using reciprocating engines as its power plant. Here, I have shown you the cross-section of a typical unit of a piston engine. Let us see the parts of an engine. This is the inlet valve, the cylinder. This the spark plug to initiate the ignition process. The piston which absorbs the pressure and converts to motion. The piston rings prevent gases to escape the combustion chamber. The combustion chamber is the place where the air-fuel mixture burns. The connecting rod connects the piston to the crankshaft. The outlet valve. Crankshaft converts the reciprocatory motion to rotatory motion. Here, I have downloaded some pictures of the parts of the engine, just to give you an idea. Here, I have shown a picture of an engine. Let us understand some terminologies. We know that the piston travels in a reciprocatory movement within the cylinder, to and fro motion. Imagine the engine placed in a vertical orientation. Firstly, the top dead center, the TDC. It is the position of the piston when it has traveled to the topmost position within the cylinder. Next, the bottom dead center, the BDC. It is the position of the piston when it is at the bottommost position. The stroke. It is the length of travel of the piston from BDC to TDC. Swept volume. It is the volume swept by the piston when it travels from TDC to BDC. Appreciate, it is the product of the area of the piston and the length of the stroke. A full cycle of the complete process consists of the piston traveling 4 times, alternately, top to bottom and back. Each travel from one dead center to another is a stroke. Thus, there are 4 strokes in a complete cycle. These are the induction stroke, the compression stroke, the power stroke, the exhaust stroke. We shall see these in detail. First, let us see the induction stroke. During this stroke, the air-fuel mixture is inducted into the cylinder. Of course, the inlet valve is already open. The piston moves from the TDC to BDC, causing a suction in the air-fuel mixture is drawn inside the cylinder. The crankshaft rotates by 180 degrees. This is broadly what happens during the induction stroke. The compression stroke. The main function of the stroke is to compress the air-fuel mixture to the maximum so as to have efficient combustion. The piston travels from BDC to TDC. Somewhere during its travel, the inlet valve closes, creating an airtight chamber. This allows for the compression of the mixture. Appreciate that the crankshaft has rotated by another 180 degrees. Just about around this time, a spark is ignited at the spark plug. This causes the compressed mixture to combust and the chemical energy is released in the form of heat and pressure energy. The high pressure energy generated pushes the the piston from TDC to BDC. This is from this stroke that the power is drawn. Enormous heat is produced. This causes heating up of the engine parts, including the piston and the cylinder. It is for this reason the cylinders are constructed with fins to provide maximum surface area to dissipate the heat. The crankshaft has rotated by another 180 degrees. By the end of the previous stroke, the entire mixture has been burnt. Well, mostly. That will depend upon the mixture setting and other design factors, about which we shall learn in another class. The burnt mixture needs to be evacuated out of the cylinder. The outlet valve is opened, enabling the burnt mixture to be sucked out and thrown out. The piston moves from BDC to TDC, pushing out the mixture. The crankshaft has rotated by another 180 degrees. We just saw an entire sequence of the 4 strokes of one cylinder. In practice, several cylinders are precisely constructed and linked to the crankshaft to work as a single unit. The orientation of cylinders, the number of cylinders, the order of the different strokes are considerations of design factor which will vary from engine to engine. One of the important design factor is the valve timing, and I shall explain it in detail here. We learned that a complete cycle comprises of 4 strokes of 180 degrees, making it 720 degrees for the complete cycle. In this diagram, the circle depicts the cycle of strokes, with the top point representing the TDC and the bottom representing the BDC. The 4 strokes will be the circle measured twice, that is 720 degrees. Let us discuss the operation of the inlet valve. The inlet valve needs to be open to induct the air-fuel mixture. The valve opens approximately 28 degrees before the piston reaches TDC while on its upward travel from BDC during the previous exhaust stroke. It remains open during the entire travel of the piston, traveling from TDC to BDC during the induction stroke. It further remains open for another 71 degrees of travel from BDC of the compression stroke. It is at that point the inlet valve closes. Now the exhaust valve. The exhaust valve opens after about 102 degrees, just as the combustion has taken place. The piston is moving from TDC to BDC during the power stroke. It remains open during the entire exhaust stroke when the piston moves from BDC to TDC. Further, it remains open for another 45 degrees after the induction stroke has begun. Now, if both the valve operations were to be superimposed, we get this figure. Notice the areas where the inlet valve and the exhaust valve remain open. For almost 73 degrees and 149 degrees as shown in the picture. This is called the valve overlap. Another important concept that needs to be explained is the spark timing. Appreciate the air-fuel mixture is ignited at the spark plug only. The flame which is consequent to burning of the mixture has to travel for the full compressed mixture to be burned. The flame for the fuel used in pistons, that is the avgas, travels at approximately 12 feet per second. Therefore, the spark timing would normally be advanced to enable complete combustion process. The actual timing itself may vary. A measure of efficiency of the engine is the compression ratio. It is defined as the volume of the cylinder when the piston is at BDC to the volume of the cylinder when the piston is at TDC. engine working is called the Otto cycle. Have a look at the graph. On the x-axis is the volume and the pressure is scaled on the y-axis. Notice the points marked by 1 to 2. This is the induction stroke where the pressure inside the cylinder remains constant but the volume increases. Next is the line from position 2 to 3. This depicts the compression stroke where the volume reduces and the pressure increases. From 3 to 4 is the combustion process. The pressure rises considerably at constant volume. From 4 to 5 is the adiabatic process of the power stroke. Can you appreciate the change in pressure and volume? Heat loss takes place from position 5 to 6. The exhaust stroke is depicted from position 6 to 1.
Thank you.